In organic chemistry, we are very concerned with the behavior and properties of electrons in organic molecules, and so we quite frequently depict the movements of electrons, both in organic reaction mechanisms and to show the interconversion or electronic relationships, if you like, between resonance structures. And there is a convention or a formalism that we use to show the movements of electrons in organic molecules called the curved arrow formalism, and we're going to introduce that here. So curved arrows are used to represent the movements of electrons both between resonance forms and in the elementary steps of reaction mechanisms. So we use them kind of in two realms, and we're going to focus on the resonance application here and move into mechanisms later in the course. We use them for the interconversion of resonance forms, and here they're purely a bookkeeping device showing the electronic relationship between two resonance forms, if you like, how we can push electron pairs around to convert one resonance form into another, knowing, as we should based on resonance theory, that this is not a physical process. This is just a device for us to help see the relationships between resonance structures and confirm that they are in fact related as resonance forms. In reaction mechanisms, curved arrows actually can have a deeper physical meaning, and we'll have more to say about this later when we get into reaction mechanisms later in the course. Now, the basic convention with curved arrows is that they show the movement of electrons. And this is important to keep in mind. We're not drawing an arrow to depict the movement of an atom. We're showing how electron pairs move. And so curved arrows always start at a concrete electron source, something you can see in a Lewis structure or bond line structure, a line or a pair of dots, a lone pair, a pi bond, or a sigma bond. This is where the tail, or the start of the arrow, appears at a concrete electron source. So for example, we might start at a pair of dots in a Lewis structure. We might start at a double bond. These are the two most common electron sources, with sigma bonds a lot less common. We always end at what I call a good electron sink. And this is a place where electrons can go, first and foremost, not to violate the octet rule, and secondly, where they're generally relatively stable, relatively happy. Something like an electrophilic atom or an electronegative atom, or we can also land electrons between two atoms at which a bond forms, as long as we don't violate the octet rule in doing so. And these electron sinks are essentially places where electrons want to go. When we get into reaction mechanisms, we'll see that this is a big driving force behind tons of organic reactions. Any sort of Lewis acid-base organic reaction can be thought of as a flow of electrons from an electron source, which we'll call a nucleophile, to an electron sink, which we'll call an electrophile. For now, though, let's constrain ourselves to using curved arrows in resonance forms. When using curved arrows to show the relations of resonance forms, here are a couple of things that you want to avoid. Avoid breaking single bonds. While this is not, strictly speaking, forbidden, it's a good practice to get into because the cleavage of sigma bonds between resonance structures generally does not lead to significant alternative resonance forms. So here, for example, we might think about breaking this sigma bond like this. And let's take a moment to appreciate what this curved arrow is telling us to do. It's telling us we're going to take this pair of electrons in this single bond, and we're going to move that pair into a new bond here, breaking the bond here and forming a new double bond here. This has the effect on the formal charge of putting a positive formal charge where the bond broke and we took the electrons away, right? So we're basically saying we're going to keep that pair of electrons at this carbon in the new pi bond. We're going to leave the other atom in that bond bereft or lacking electrons. But this shows the cleavage of a single bond. And so this alternative resonance form is actually not a significant contributor to the true or quantum chemical structure of this cation. And so we want to avoid, and this is generally true, that when you break single bonds like this, you're not generating a significant or important alternative resonance contributor. So you want to avoid this. It tends not to generate important resonance forms. The second rule is more important and is definitely something that you should absolutely avoid. Never exceed an octet of electrons at a second row element. For example, if we think about what's going on here, this arrow is telling us to take this pair of electrons on the oxygen and create a new CO double bond. That's the only arrow that's shown. this carbon is already satisfying the octet rule. So if we give it another bond, we're going to generate a structure with a mortal sin of organic chemistry embedded in it, 5 bonds to carbon, and you want to avoid that. This arrow in isolation is problematic. Now, as we'll see, you can use multiple arrows in a single electron flow. If we continued the electron flow, for example, kicking electrons here, if that were a double bond, for instance, that would potentially be valid. Now, with the H there, that's going to break a single bond, and that violates rule 1, so bad electron flow here. And the other 2 examples, I'd encourage you to pause and draw out the results of these electron flows and convince yourself why these electron flows are not good, not going to lead to significant resonance contributors, and these are going to produce structures that have problems with respect to the octet rule. So rule number 2 tells us that we need to avoid violating the octet rule by putting more than 8 electrons at a second row element. But fewer than an octet of electrons is actually completely okay, and we'll see this at numerous occasions throughout organic chemistry 1 and 2, that we can take, for example, a pi bond and simply push the pi electrons up to one or the other of the atoms involved in the pi bond, and this generates a resonance structure that's completely fine. And we show this with the curved arrow formalism by starting electron flow at the pi bond and sending those pi electrons to one of the atoms in the pi bond. So here, for example, this is a carbonyl group, and the oxygen, being more electronegative than the carbon, actually has higher electron density than the carbon. And this curved arrow is showing the generation of an alternative resonance form where we kind of emphasize that oxygen is negatively charged and carbon positively charged in the carbonyl group. And this is completely fine. Nothing wrong with that at all. You can always push pi electrons in this way, and generally the way you want to do it is push those pi electrons to the more electronegative atom in the bond. Okay, let's practice a little bit with the curved arrow formalism, looking for good and bad electron flows and rationalizing in each case why the electron flow is valid or invalid. Okay, let's start with A. Now A, the thing we should notice is this nitrogen is already satisfying the octet rule, and it's already saturated, right? It's got 4 single bonds. And so this electron flow would establish a 5th bond at that nitrogen, and that's going to be problematic. So this is invalid electron flow. We got a bad electron sink there. That positively charged nitrogen, despite the positive charge, is a poor electron sink because it's saturated and already satisfying the octet rule. Okay, what about E, just below? I'm going to go vertically down the rows, down the columns here. So in E, we've got completely fine electron source in this O's lone pair. It's heading into a new double bond or a new pi bond here. But notice, the carbon where those electrons are headed is already saturated, 4 single bonds. This electron flow would add a 5th bond to that carbon. That carbon would be violating the octet rule. It would be a Texas carbon, and that's a no-no. So that's out. What about I? Well, in I, the electron flow arrow is telling us take this pi bond in the CN triple bond and send it into a lone pair on the nitrogen atom. This is completely fine. This would make the nitrogen formally negative, add a lone pair, essentially convert a bond at the nitrogen into a lone pair, decreasing its formal charge by 1 unit. This would make the carbon positively charged, and that carbon would have fewer than an octet of electrons, but this is okay, right? And so the electron flow in I is completely fine, and it's actually highly analogous to what we did up here, simply pushing pi electrons to the more electronegative atom in the bond. B is likewise extremely analogous to what we did up here. We're just taking the CO double bond electrons and sending them up to oxygen. This would generate a C plus O minus resonance form that we've already discussed is valid. Now, when you're thinking about and looking at electron flows, it's often very helpful to draw in hydrogens in the vicinity of where you're pushing electrons. And I've done that in F and some of these other examples. For example, in F, it's very important for us to notice that where we're sending electrons is already saturated, right? It's got 2 H's there. It's satisfying the octet rule with 4 single bonds. So that's not a good electron sink. This would add a 5th bond to that carbon, and so the electron flow in F is invalid. In J, we are taking pi electrons between the 2 nitrogens, and we're sending them onto this nitrogen with positive charge. So this would have the effect of putting positive charge on this nitrogen on the end, making this nitrogen neutral, adding a lone pair of this nitrogen, and taking the triple bond down to a double bond. This is actually completely valid. Now, this may give you a bit of pause in that this nitrogen is going to end up violating the octet rule with fewer than 8 electrons. This is marginally okay. In this particular case, it turns out to be okay. And when you talk about diazoniums, aryl diazoniums in organic chemistry too, you will see that the alternative resonance form that comes from this kind of electron flow is actually very important to consider in certain types of reactions. All right, let's move on to C. C, again, where we're sending electrons, is already saturated with 4 single bonds, and this electron flow would add a 5th. That's a no-no. G, we can actually look at the electron source and immediately rule out this electron flow. This involves pushing a single bond, breaking a single bond, and in resonance electron flow, that is a no-no. That's not going to lead to a significant alternative resonance contributor of this molecule, so that electron flow in G is invalid. K has now our classic saturated carbon here, and so that's going to be a problem to send electrons to that. That would create a Texas carbon. And with all of these, again, with all these problematic electron flows, I encourage you to actually draw out what the arrow is implying and make sure you understand why that structure you're drawing is not a valid Lewis structure or is a non-significant resonance contributor. So K, invalid. D is an interesting one where this oxygen has 2 lone pairs and 2 single bonds. And so it is actually saturated, right? All single bonds, all lone pairs, no pi electrons at that oxygen that we can potentially push. And so this curved arrow, while the source is completely fine, source is a carbon-carbon pi bond, this would add a 5th pair of electrons to the oxygen, giving it 10 total electrons, violating the octet rule in a problematic way. This is invalid electron flow. H is another good example where drawing in implied hydrogens helps a lot. We want to draw in these methyl hydrogens to help us see that this carbon is saturated with 4 single bonds, and so not a good electron sink. This would create a Texas carbon. That's a no-no. Also, electron flow is starting at a single bond, which is a no-no in resonance, as we looked at in rule number 1 on the previous slide. So that's out. And finally, L is very similar to the previous case, except here the electron source is fine. It's a lone pair, but we're trying to send electrons again to that saturated carbon atom with 4 single bonds. This would create a 10 electron Texas carbon. That's going to be invalid electron flow. So this is just kind of getting us warmed up with curved arrows, and a number of these flows are invalid, and it's important to avoid these kinds of pitfalls when you're using curved arrows. Keep in mind that we're showing the movement of electron pairs here as well, and that we, from the sort of instructions provided by the curved arrow, we can draw a structure, right? And this is a nice example illustrating how to do this. We can draw a structure that comes from sort of following the instructions embedded in the arrow. This is the beauty of the curved arrow formalism. More often than not, we don't just use one curved arrow to show electron flow or electronic movements or the interconversions of electron flows. We can combine curved arrows with each other to show multiple electron pairs kind of moving or flowing, as we like to describe it, across a molecule. I think about a waterfall or the flow of water down a river, right? Electrons do the same thing in reactions, and at least in our heads in resonance forms, even though we understand that physically speaking, those electrons are smeared out over all the atoms involved in the resonance. And the idea here is the same as we've been talking about. Electron flow starts at an electron source, generally a lone pair or a pi bond, and it ends at an atom that can hold a pair of electrons, an electron sink, an electronegative atom, or a bond between 2 atoms that does not violate the octet rule on its formation. So an example of multi-electron pair electron flow is shown right here. Notice that if we just looked at this arrow in isolation, it looks like an invalid electron flow, but we're sending electrons to an unsaturated atom that has pi electrons that can be pushed further. And so combining this arrow with electron flow that lands on the carbon sort of on the far side of the double bond is valid and produces a completely valid and actually quite important alternative resonance form of the starting molecule. We'll talk about how to recognize this kind of electron flow here in a second. Our really focus for the time being is on recognizing how these curved arrows imply this structure, right? They're telling us, hey, take this lone pair and make a new NC pi bond. Take this pair of electrons and make a new lone pair on this carbon. And the changes in formal charge are worth noting as well. We've converted a bond into a lone pair. That increases the formal charge by 1 unit. And in converting a, sorry, I said that backwards. In converting a lone pair into a bond, we increase the formal charge by 1 unit. In converting a bond into a lone pair, we decrease the formal charge by 1 unit. This is a general pattern that you'll see, and it falls out of the bookkeeping, electronic bookkeeping associated with curved arrows. Okay, there's another alternative resonance form that we can draw starting with this structure and thinking about what else we could do. Now I see a CN double bond. I could push those electrons up to the more electronegative positively charged nitrogen atom and generate an alternative resonance form where we've turned this bond into a lone pair at the nitrogen, so the nitrogen is now neutral, and we've taken a bond away from this carbon, and so that carbon is now positively charged. All three of these structures are valid and significant, I would argue, resonance contributors to the structure of this molecule. So what we're seeing here is that often multiple valid resonance forms are possible for a structure. And what we can do is we can sort of interrupt electron flow, right? We could have, for example, gotten directly from that first structure to this one simply by omitting this arrow right here, right? You can verify that this leads to that structure on the right directly. And these are all valid resonance forms, and the kind of order in which we show them and how we move electrons is not so important as long as we recognize eventually all of those resonance forms. And I wanted to work through an example of this with a highly delocalized molecule with multiple resonance forms to kind of show you how this works. So one way we might approach this is by saying, okay, I see a good electron source in the pair of electrons on the oxygen, one of the oxygen electron pairs. So I'm going to start by pushing that in. Now, this arrow by itself is not valid, right, because I'm already satisfying the octet rule here, but I could continue to push these electrons. I could land them on this carbon here, and this would create an alternative resonance form, and I'm just going to use copy and paste here to save myself a little bit of time. This would create an alternative resonance form where this pair of electrons has been converted into a double bond, and this pair of electrons has been converted into a lone pair. And this is, while not the best resonance form, a completely valid resonance form. We could then notice, okay, I've got a lone pair adjacent to a carbocation, a positively charged unsaturated carbon. So I could flow electrons like this and generate yet another resonance form where I now have a CC double bond there. Notice what this is telling me is take that pair of electrons and make a new pi bond. Of course, I could have gone directly to this structure on the far right by, instead of landing on this carbon, sending the electrons just between the two atoms like this. That would get me directly to this structure on the far right. That's completely fine to do as well. So there's some flexibility built into the curved arrow formalism when you're drawing resonance structures. Don't feel like you need to step through the electron flows in a particular way. The first sort of valid electron flow that you see, you can start there and then look for other possibilities when you're drawing resonance forms. It's entirely up to you. And there are even more possibilities starting from this resonance form. For example, I could simply push the CO double bond electrons or pi electrons up to oxygen, generate a carbocation right here. And I'll leave it at this, but if you want some more practice with resonance, this is a good opportunity to pause and see if you can draw all of the alternative resonance forms of this cation. It's a great exercise in recognizing and drawing resonance structures. And there are several more than the structures I've drawn here. We've alluded to this idea already that pushing electrons causes changes in formal charges where we convert bonds into lone pairs or lone pairs into bonds, or we take, for example, a carbocation and add an additional bond to it. So you want to carefully evaluate formal charge in the resonance structures that you draw. And the example electron flow on this slide is going to give us some practice with this. So let's start by sort of following the instructions implied by these curved arrows and drawing the alternative resonance form that results. So first, I'm going to add in the implied hydrogen at this carbon where we're landing electrons, just to make sure that we don't lose that when we're looking at formal charges. Okay, so the electron flow is telling us here we're going to take a lone pair and convert it into a double bond. And we're going to take this CC pi bond and we're going to land those electrons onto this carbon. And I've gone ahead and added the formal charges, but this is a good opportunity to pause and verify on your own that these formal charges are correct. The oxygen is formally positive, and this carbon is formally negative, and the carbon at the center, which is maybe not directly involved in the electron flow, but is sort of in the river, right, so to speak, if we're thinking about the electrons flowing like this, is neutral. Starts neutral and ends neutral. All right, so what are we noticing here? Well, let's focus on the start of electron flow first. Pushing a lone pair into a bond, taking this pair of electrons and pushing it into a new bond results in an increase in formal charge at the atom that donated the lone pair, in this case oxygen. So we can see, for example, that the oxygen starts neutral in the initial structure and in the generated resonance form now has positive charge. The formal charge has increased by 1 unit. And this is really just a consequence of the electron counting, accounting and how we think about formal charge. Pushing a bond into a lone pair results in a decrease in formal charge at the atom that accepts the pair, which is this carbon right here in this case. So notice we go from neutral to negatively charged at this carbon. That acceptor atom has decreased in formal charge by 1 unit. And again, because of the way we calculate formal charge and account for electrons, pushing a bond into a lone pair on an atom will always result in a decrease in formal charge like this by 1 unit. Notice also what's happening at that central atom. Shifting a bond about a central atom from one atom to another causes no change in formal charge. This carbon highlighted in purple starts neutral and ends neutral. Really, its electron count has not changed at all. All that's changed is the position of the double bond about that carbon atom, right? And so it starts neutral, remains neutral. No change in formal charge at the central atom when we flow electrons like this.